Here we specialize our discussion into the case where the domain and the codomain of a linear transformation are equal. Now suppose V is a vector space of finite dimension, then the function that sends a vector in the domain into itself is a linear transformation denoted by ID. We call this the identity transformation. In fact, this linear transformation defines an isomorphism between V and itself. Now suppose that we have two ordered bases for S, or rather, for the domain, we have S, and for the codomain, we have T. Then our previous discussion tells us that we can represent this linear transformation by a matrix. The matrix of the identity transformation with respect to S and T is the n by n matrix whose entries are obtained by finding the coordinate vectors of each vector from S with respect to T. Okay, so the first column is the coordinate vector of V1 with respect to T. The second column is the coordinate vector of V2 with respect to T, and so on. Recall that the coordinate vector of the image of V under the linear transformation with respect to T can be obtained by multiplying the coordinate vector of V with respect to S by the matrix of the linear transformation with respect to S and T. So we just multiply this matrix by the coordinate vector of V with respect to S. But here note that the thing inside, the image of V under the identity transformation is just V. So this formula provides a relation between the coordinate vector of V with respect to T and the coordinate vector of V with respect to S. This motivates the following definition. So here the n by n matrix, which is the matrix of the identity transformation from S to T, will be called the transition matrix from S to T. So essentially, this is the matrix that we use to transfer vectors in the span of S into vectors in the span of T. We emphasize that in the transition matrix, the jth column is the coordinate vector of the jth vector in S with respect to T. Okay? So we mentioned that this first column, this is the coordinate vector of V1, no? The first vector in S with respect to T. This is the coordinate vector of V2 with respect to T, and so on. Note that the columns in the transition matrix from S to T are linearly independent because they are coordinate vectors of basis elements. And so the transition matrix from S to T is invertible. And the inverse of the transition matrix from S to T is the transition matrix from T to S. Suppose we have a vector space with ordered bases S and T. So S has elements V1, V2, V3. T has elements W1, W2, W3. Let's suppose that V1, V2, and V3 are given by these linear combinations of elements from T. So these relations actually give us the coordinate vectors of V1, V2, and V3 with respect to T. Okay, the first equation tells us that the coordinates of V1 with respect to T are 1, 0, -1, because the coefficient of W1 is 1, coefficient of W2 is 0, and the coefficient of W3 is -1. And similarly, for V2, the coordinates with respect to T are 2, 1, 1. For V3, the coordinates are 3, -1, -5. And so, the transition matrix with respect to S and T is the matrix of size 3 by 3, whose first column is the coordinate vector of V1. The second is the coordinate vector of V2. Third column is the coordinate vector of V3, all with respect to T. Now, if V is a vector such that V is V1 minus V2 plus 2V3, so meaning the coordinate vector of V with respect to S is 1, -1, 2. Then the coordinates of V with respect to T can be obtained using this formula. So we just apply this matrix to the coordinate of V with respect to S, rather the coordinate vector of V with respect to S. You can check that the result is the vector with entries 5, -3, -12. So this is the coordinate vector of V with respect to T. So in other words, as a linear combination of elements from T, V is 5W1 plus -3 times W2 plus -12 times W3. So we know that this matrix allows us to transfer vectors from the span of S into the span of T. So how do we reverse that process? Meaning, how do we transfer vectors from the span of T into the span of S? Well, if W is a vector such that the coordinates with respect to T is known, then we can obtain the coordinates of W with respect to S by manipulating this formula. So we know that the transition matrix is invertible. So in this equation, we can multiply both sides by the inverse of the transition matrix from S to T on the left side. Okay, on the left. Okay. So we multiply by the inverse on the left. So here, the product of this by this is just the identity matrix. So the left-hand side is just reduced to the coordinate vector of W with respect to S. Okay, so we just need to determine the inverse of the identity transformation, rather. We just need to determine the inverse of the transition matrix from S to T. And you can obtain that inverse using Gauss-Jordan. So I will leave the details as a reading exercise. So you can find it in the module. But here we find that the inverse of the transition matrix from S to T is given by this 3 by 3 matrix. And we noted that this inverse is the desired transition matrix from T to S.